Hello and welcome to the Daily Space for today. Oh, I still have music running in the background. Let me turn that off. Hello and welcome to the Daily Space for today, April 17th, 2019. I am your host, Dr. Pamela Gay, and I am here to put science in your brains. Now, we started a few minutes late today because, oh my God, there is so much news. Like many of you out there, I was glued to the news this morning, and in my case, it was listening to the radio. And while I was listening to the radio, I kept getting beep after beep after beep as new press releases came in. So I'm going to try and make it through all of it, but I have to admit there was more news than I could completely read. So bear with me as to a certain point, we all work on learning this together. In today's first story, we have news about a new way of detecting neutron star collisions. Recently, while making completely unrelated observations of a field of view that we are seeing here, Chandra X-ray Observatory caught this bright flash that was associated with a galaxy 6.6 billion light years away from Earth. And this bright flash was the kind of bright flash that we hadn't seen before. And when the scientists went diving through the literature, looking to see what theories might explain what had been seen, they found that their observations matched, well, ideas of just what a neutron star collision would look like if viewed in the X-rays. Now, this is the kind of brief flash that occurs for a moment in time that, were we close enough, would have also been observed with gravitational waves. This time, there weren't gravitational waves going along with the detection. Our current capacity just doesn't allow that. But this is another neutron star collision. The scientists associated with this particular event believe that after this merger occurred, what was left behind was a new neutron star, even more massive than before, rotating ever so fast with a powerful magnetic field. So it may be good that this is 6.6 billion light years away. So kudos to those scientists for seeing something they didn't expect, figuring out what it is, and giving us a new insight onto the evolution of stars. Now, these are presented in no particular order today in another piece of news. And here I'm going to give you the URL. We have what to me is the most confusedly named project of the year. You may know there is a spacecraft called OSIRIS-REx that is at this moment visiting the asteroid Bennu. You may also know there was a spacecraft called Rosetta that visited the nicknamed Churyumov 67P comet, officially known as 67P, Churyumov-Gerasimenko. Rosetta took 70,000 images of 67P. Let me say that again, 70,000 images. And all these images can be yours on the OSIRIS image server that has nothing to do with the OSIRIS-REx spacecraft. Its data will go elsewhere. So if you want to explore the Rosetta images of 67P, go to the OSIRIS image server that has nothing to do with OSIRIS-REx. You will not be sad. You may remind yourself that astronomers shouldn't be allowed to name things. So it is awesome to see all of this data put out into the public domain. And kudos to the European Space Agency for making this so easy to interact with. In other news, because wow, there's news today, we have an artist's rendition of a tiny star behaving badly. 250 light years away from us is the mouthful of a name ULASJ 224940.13-011236.9. This little tiny star, back on August 13th of 2017, let off a flare 10,000 times more powerful than what we typically expect to see from the sun. This particular star is cooler and smaller than what anyone expected this kind of a flare to come from. What we're dealing with is the smaller you get, the, well, smaller your magnetic field should be. It turns out we were wrong. This star is a tenth the radius of the sun. And sorry, I misstated the 10,000 part. It was 10,000 times brighter than it normally is during the flare. And this was 10 times more powerful than the Carrington event, which is the brightest recorded solar flare from our sun. So this star, 1/3 the size of our sun, flared to 10,000 times brighter than normal for one brief, deadly moment. And that flare was 10 times more powerful than the largest flare our much bigger sun has been observed to have. In other units, this was 80 billion megatons of TNT worth of energy. Now, while it is in general cool to bring up the largest, brightest, smallest, fastest, thank you so much, Magic, for the follow. Thank you. While it's generally just cool to bring up the largest, smallest, all these different Guinness Book of Stellar Extreme records, one of the reasons we bring this up is, well, we knew that red dwarf stars were angry stars that flared all over their nearby planets for a few billion years. It was thought the smaller ones would be a bit calmer. We were wrong. And this has implications for just where life can easily form. I'm not going to say it has implications for where life can form, because even on our own planet Earth, it appears life will form where life wants to form, including like in places where it eats radiation. But it seems that there are certain conditions where more life exists and certain conditions where less life, extremophile life, exists. And a world that is getting flared upon with this much energy, probably gonna be harder to form life on, especially where we're talking about a little tiny star. So to have liquid on your surface, you're gonna have to be a whole lot closer, because if you're too far away, you freeze. And admittedly, if you get too close, you evaporate everything. Look at Mercury. But it's still not where you want to be when one of those flares goes off. So way to go, ULASJ 224940.13-011236.9. You are a record setting, forcing us to rethink little star that has one heck of a magnetic field for which you are to be studied. In other news, we have research spanning the decades, and I mean this quite literally. A team of astronomers from UNIGE has discovered 5 new planets that have orbits that are 15 to 40 years in duration. Now, saying that there's 5 new planets is not newsworthy anymore. We find planets constantly. But it turns out we've only found 26 stars in all the years, not stars. We've only found 26 planets in all the years that we've been looking that have periods greater than 15 years. These 5 stars, they have masses ranging from 3 to 27 times the mass of Jupiter. They're massive. They can be directly imaged. And in order to be able to detect them, there had to be a dedicated telescope. This isn't the kind of thing that you can do with most telescopes. It isn't the thing where you get 3 nights a year, you look hard. It isn't the kind of thing where you share your observations with the entire rest of the sky like Tess. This is the kind of thing where you look night after night after night. This work from the University de Geneva, UNIGE, was performed using the Euler telescope, which is at La Sille in Chile. And I love the way that it's described. One of the observers, Emily Rickman, says it took 20 years and many more observers. This result would have been impossible without the availability and reliability of the Crowley spectrograph installed on the Euler telescope. And then she goes on to talk about how essentially the astronomers just took turns sucking it up and observing night after night, year after year to get these results. So sometimes hard work pays off and gets you these really under-observed planets that are more like the planets we're used to. These are the worlds that have the longer orbits like we see in our own solar system. So kudos to this team for your patience and your hard work. To remind everyone, the first planet around a normal star was only found in 1995. So we haven't been looking for that long. We generally expect planets that are detected to either have 3 transits or 3 orbits detected through a Doppler shift. This means you have to see them through 3 cycles of their period. And it's only through direct observation that we're allowed to see a planet with an orbit of 40 years in less than 20. So well done. Kudos. I don't even know what to say for how hard and awesome the work they did happened to be. Now, in other news, I told you there was a lot of news. Another star has brought us new and awesome science, and it is yet again a little tiny star. Now, the reason this one needed to be a little tiny star is so that it could live a good long time and allow us to peer into, well, the atomic composition of our early universe. This particular star, J0023 plus 0307, is the star with the least amount of stuff that isn't hydrogen and helium that we know of. We refer to everything that isn't hydrogen or helium as metals because astronomers, well, that's just what we do. And this extraordinarily low metal ratio indicates that it formed out of a lot of the stuff that was left behind by the first generation of stars, and a lot of the stuff that was left over from the Big Bang, and a tiny bit of stuff that was left over from the first generation of stars. Now, generally in stars, lithium is destroyed. And so when we look at stars, we very carefully measure the ratios of carbon to lithium and many other different atoms. And we use this to build a picture of how much recycling of the material has occurred and what this can tell us of Big Bang nucleosynthesis. Big Bang nucleosynthesis is that process that occurred early in the first 3 minutes of the universe, where the entire universe was so hot and so dense that nuclear reactions could take place, much like what happens inside the core of a star. For a brief moment in time, we had hydrogen that formed naturally from protons and electrons hooking up, and we had helium that formed through nuclear processes, as well as trace amounts of lithium and beryllium. Beryllium gets formed in stars. It's kind of annoying that way. It makes it much harder to use as a probe of Big Bang nucleosynthesis. But that lithium, well, what we measured here didn't quite match what was expected from Big Bang nucleosynthesis theories. Now, this means that we either don't fully understand the origins of this star, which is possible, or we have an overestimation of how much lithium is produced during the Big Bang, which is also possible. And this kind of moment is what keeps us looking as scientists. We don't understand everything. We have theories, we have to test them. And when we find data that doesn't quite match, that isn't to say our theories are wrong. It's to say we need to look harder, look more, and look at all the theories involved. So where we got wrong, that's where the really interesting new science is going to be found. So I look forward to coming years seeing more and more research into what could have created this amazing little star and what it tells us about the origins of our entire universe. It's a lot to put on one star, but I'm sure that, well, J0023 plus 0307 is up to the challenge. Now, in continuing news, we have an update on the planet Mercury. One of the things we do as scientists is we try to find ways to probe the interiors of planets without being able to actually go and look at the interiors of planets. One of the ways that we do this is we look at how they rotate and how their rotation does what we call precessing. So if you have a rotating world, in this case, I'm trying to find something that I can easily do a demonstration with. I'm going to use this wonderfully asymmetric bull clip. Thank you for the follow. And the reason I'm using this asymmetric bull clip is because I can show you it's rotating, and I can also have it rotating and have its rotatingness rotate. That exaggerated movement of the top, which you see with spinning tops on tables, is called precession. And the exact physics that describes how this rotates and how its rotation precesses has, well, a lot to do with the interior of the object. If you have something filled with liquid, it's going to spin differently from something that's completely solid. And as you go from having a liquid core to have a solid core, your spinning changes. Now, some of you may know this from cooking, where you can tell if an egg is hard boiled by spinning it on the counter. So if it's Easter egg painting season in your household and you don't remember which ones you boiled and which you didn't, give them a good spin. The hard boiled ones spin better. Well, it turns out that Mercury spins better as well because it appears to have a solid core. And this is measurements that were performed by the Messenger mission, a NASA spacecraft that went and visited Mercury and which still is yielding new science results years after the mission came to a close. So by carefully studying the wobbles in the rotation of this world, scientists have been able to basically say this is a solid center, a outer molten core, and a solid crust. This is mathematically the most annoying moment of inertia to have to calculate for a, well, spherical object, but it is scientifically kind of awesome. Okay, and in continuing news, for the first time ever, scientists have been able to identify the first possible molecule our universe could have formed, and it's a molecule that your chemistry teachers wouldn't have taught you about, because if you're like me, you learned that atoms like helium, these noble gases, they don't work and play well with others. And this means that we just don't have, most of the time, atoms involving helium. Well, in this research coming to us from the folks at the Sophia Airborne Observatory, we have learned that helium hydride, a molecule involving helium and hydrogen, we have learned that this particular finicky molecule, which was first theorized back in 1925 and created in a laboratory, it's now been detected in the early universe. So we now know, as is shown in this artist's rendition, that these atoms are out there waiting to play their role in the chemical evolution of our solar system. It's kind of amazing that it took almost 100 years from that 1925 lab creation across all the decades of staring out into space to find this molecule occurring in the wild. As always, our universe is an amazing place filled with the unexpected. And if you have a kiddo looking to do a report on some molecule, this is a molecule I recommend because, hey, it's a great way to, well, show their teacher that one of those things that gets taught has an amazing exception. Helium does exist, at least in this one crazy and awesome molecule. And finally, I have something that isn't so much a science story as just a pretty picture, and that's okay. It is Hubble's 29th birthday. Next year, Hubble, well, gets to start worrying about all the adulting that comes with being 30-something. And, well, that's a pretty good ride for a spacecraft. And they are celebrating their 29th birthday with this amazing image of the Crab Nebula. This southern hemisphere object is just pretty. And Hubble sometimes will make the choice to take these deep and amazing images of these objects so that, well, first of all, we can go, oh, pretty. That is a legitimate thing occasionally. But also so we can get a better understanding of what's going on in the system. This Southern Crab Nebula, it has a red giant star and a white dwarf. And the red giant is shedding its outer layers, and these are getting strewn out and ejected and sometimes pulled on to that white dwarf companion. And all these different combinations, the outbursts of the white dwarf, have led to this amazing system. And with this high resolution graphic, we'll be able to match our theories of how systems like this function, what occurs, how things are ejected. We'll be able to study how well our theories hold up when given a deep and beautiful picture of reality to compare with. So thank you, Hubble, for sharing this bit of beauty on your birthday. I can't believe how old you are. I say that with love. Okay, that concludes our science for today. I'm going to thank all of you for being here and ask, hey, give us a follow over on YouTube. If you miss our shows live on twitch.tv, where you can now start typing in your questions, just remember to @me at CosmoQuestX. Thank you, Lancy, for subscribing here on Twitch. Thank you. If you subscribe over on YouTube, first of all, I have a really cool graphic that I'm proud of. Thank you, Trekker Kev, for the bits. I have Cheerios I can throw to my dog. I think there's still a dog up here. We'll find out in just a moment. If my computer can succeed. There it goes. Oh, I'm being stared at. So, please, if you give us a follow over on YouTube, first of all, it will trigger a fabulous new animation. And second of all, it really helps our channel. And we are always there for you to catch up on later if you miss us live. Thank you, Veronica. I'm going to mute my mic for a moment and call the other dog. For those of you who are new to the channel, the way we say thank you is by giving you cuteness in the form of pupsters eating Cheerios. So thank you for all that you do to keep us going. We here at CosmoQuest X are dedicated to providing you a place to learn and do science. And we are supported by you and produced by the Planetary Science Institute, a 501c3 nonprofit dedicated to the exploration of our solar system. Now, I saw Susie's subscription come in. There! We see Rob's. You get to see my new animation. I'm so stupidly proud of that very silly animation. I'm just going to keep throwing Cheerios to my pupster. Thank you. There's the other sub I saw. Thank you. These are the things that make me happy. We are here thanks to you. But if you can't give, that's okay. We just want you to learn, and we're cool with just hanging out and talking science all day long, every day. Keep the conversation going over on Discord. And sometimes we also just play games. So join us over on Discord and keep the conversation going. Now I am going to see what questions you have to ask. And I may have lost some of the questions at the very beginning of the show. So if I don't answer your question, wow, I managed to get Cheerios all the way across the attic. If I don't answer your question, please just re-ask it. I am going to start at the top. DPI 209 correctly points out that Osiris is the name of the camera that Rosetta used to take the images of Sherry Geary 67P. I still say it's confusing. I'm Team Osiris Rex. All right, so Hanny asks, would a Carrington event affect electronics underwater? I don't think so. I think underwater will sufficiently protect you for large enough amounts of water. Like a molecule of water probably won't cut it. But if you're like substantially underwater, yeah, that should protect you. Okay, Fenring asks, is this red dwarf rage connected to them not having a convective zone that makes energy output unstable? It appears to be related to the magnetic field rearranging. These kinds of events are driven by magnetic fields. And in this case, I have to say, we have words to describe what's going on, but our maths aren't that good. We know that solar and stellar magnetic fields are driven by what we call a magnetic dynamo, a layer of charged particles that exist midway out on these kinds of objects, and their rotation and internal interactions drive these magnetic fields that periodically turn themselves inside out, reverse polarity, and get a little tangled up in the middle. It's the breaking of those tangles that leads to massive coronal mass ejections and similar kinds of interactions. So we're still figuring it out. Thank you, Svartmaya, for the sub. Thank you so very much. At some point, I may have another dog up here. It's a beautifully rainy, cool day, which means that Eddie, the other dog, is happily outside right now. Okay. Astronomers did skip chemistry classes. We also took physical chemistry, which is really quantum mechanics. And you don't get past helium in that because it gets way too complicated. Crispy Fried Man asks, I would imagine that the overwhelming majority of material in any black hole disk would just be random passerby photons that happen to get stuck in, with the only exceptions being if an event happens, such as a star falling in very recently. Well, it's not just photons of light. It's also just the general gas and dust that is pretty much everywhere. When we look out through our galaxy, we have to take into consideration what we call reddening that occurs from this constant haze of dust in all directions. There's the other dog. I'm going to throw Cheerios to get him excited. No. Go over there. Go over there. Don't come to me. There we go. Now we have 2 grazing puppies. So these disks in around black holes consist, if it's a stellar mass black hole, often of material that was stolen off of another star through what is called Roche lobe filling. This is where you have 2 stars near one another, and the one gravitationally sucks matter off the other, stretching this one into the shape of a teardrop, which I don't have the coordination to do. And when its teardrop is completely filled, some of the material will begin streaming out and form a disk around the smaller compact object. So you can end up with a disk around a black hole that is made up of stolen cannibalistic star stuff. With supermassive black holes in the centers of galaxies, you end up with dust and gas that gravitationally got triggered to fall in when its orbits were disrupted through interactions or other events. And we don't know how many black holes are out there being what we call naked black holes. These are black holes that don't have companions and accretion disks and are just hanging out, distorting space and time as black holes do. Yeah. Thank you, Fenring, for the donation. Thank you so much. We are currently working to raise funds to make payroll. We really want to pay Annie all the hours she puts in for this channel. Please help us do that. It is donations like Fenring's that really make the difference. Also, we have a Patreon, patreon.com/CosmoQuestX. And if you subscribe on Patreon, it's a recurring payment, but we also send you shit. So if you want Christmas cards and things like that, sign up on Patreon. Okay, back to the science, which is what I really like. Okay, Henny goes on to say, what is the likelihood of any red dwarf nearby was formed right after the Big Bang? Shouldn't they still be around? Yes, any red dwarf star that formed immediately after the first generation of stars should still be around. It's that catch of after the first generation that makes it hard. So in order to get small stars, it looks like you probably need to have heavier elements. And the processes that drive stellar formation and lighting up to form stars indicates that first generation of massive stars made of hydrogen, helium, and trace bits of lithium and beryllium, they would have all died quickly, going supernova before the smallest stars had a chance to form, before the smallest stars could form. And their enriched materials, their carbon, their nitrogen, all the other stuff they made would have enriched that first generation of tiny stars that formed. And we do find these tiny stars periodically. There aren't a lot of them. They tend to be dynamically tied up in some places more often than others. But because of how things form, we don't find them everywhere. The disk of our Milky Way is made more of young stars that formed recently in what are called open clusters. The outer parts of our galaxy are littered with shredded dwarf galaxies, which have stars of old, for a variety of different values of old stars. So yeah, the first generation of baby red dwarfs are out there, but they're not pure hydrogen and helium. And we are working to study them, but they're hard to find and they're not nearby. Okay, looking to see what else is in here. Crispy Fried Man asks, can getting images of black holes now advance our understanding of the still theoretical fourth spatial dimension? So I wouldn't say fourth spatial dimension. There are a number of different theories, of which who knows which one is the correct one, that say that space and time that we experience is 3 general directions and time. But in addition to these dimensions that we experience, there are upwards of 11 or more total dimensions of space that are required to explain, for instance, a lot of the particle aspects that we see. So when we see an electron with spin up or spin down, what we're actually seeing, according to some theories, is the two different ends of a multidimensional particle where the other dimensions are rolled up outside of what we experience. There's a lot of these theories. It's unclear which ones are true. And the way we really get at understanding those is through particle physics. Our images of black holes, the shadows they cast, and their event horizons that distort the space around them, these are helping us understand relativity, gravity, and no one has figured out yet how to entwine our understanding of particle physics with our understanding of gravity. And it's unclear if gravity actually can be folded in with all the other forces. Perhaps it is just the space, the shape of space, instead of so much of a force. That would be tremendous. That's a philosophical conversation. But we don't know. These are the things that we struggle to figure out. And quantum and gravity just don't want to play together. Okay, let's see what else is in here. I love scrolling through and seeing all these subs and bits, and more than that, all of the emotes. Seeing all of the emotes brings me no end of joy. Especially when we get to talk about rovers and have pictures of rovers and talk about space telescopes and have pictures of satellites. It's kind of awesome. So all of our emotes are by Austin Hinterleder. He is one of the artists behind everything we do, including most of the stuff on our Redbubble store. So yeah, I just love Austin's work. He brings me joy. Okay, Hanny is now asking, if we treated gravity as the shape of space, could we get answers to quantum relativity questions? Not that we figured out. Not that we figured out. So yeah, we just don't know. These are the things that drive us to keep doing science. And I think that brings us to the end of our new science today, because I need to go work on writing software to get you doing new science. Maybe not tomorrow, but in the not too distant future. So thank you all for being here. We will be back tomorrow at 1 p.m. Eastern, 10 a.m. Pacific. That is 6 p.m. London time, to bring you another edition of the Daily Space. In addition to this show, we also have the Sunday Science Hour at the same time, same place. And that is brought to you by Annie Wilson, who's currently working through showing how to make amazing color Hubble images like the one I showed you earlier. We also, in addition to that, bring you launches, landings, and other space-related special events as they happen. So give our channel a follow. Follows are free, and let's share the exploration of our solar system and beyond together. Thank you all so much for being here. I am now going to look for a channel to raid. Suggestions, as always, are welcome. Scrolling. The place that I go to look is the Knowledge Fellowship. It is a Discord filled with people dedicated to trying to, at least some of the time, get information into your heads. I believe that Oh Bother, who is a favorite of the channel, is streaming. Yes, he is, I think. Unless I see other suggestions, that we are totally going to raid Oh Bother. Please give him a warm rocket welcome and say hello. As always, we are brought to you by the Planetary Science Institute, working in collaboration with Youngstown State University. We are brought to you by you. It is the donations from you and people like you that allow us to keep going. And we are so very grateful. I say it every day, and I feel it every day. Thank you so much for being here. And I am now going to awkwardly figure out how to roll the credits. One of these days, I'll have this set up better. It's tradition. You awkwardly roll the credits. And my dogs are running away because there's a fire truck. So I will see you all on the other side. Bye-bye, everyone. Oh, I forgot to say what I always say. Have a fabulous morning, evening, or afternoon. And remember to go outside and look up. Bye-bye.